All right, we are live. So today I'm doing a slightly different lecture. And what we're going to do here is we're going to use Excel to explore the behavior of a feedback loop. So this is kind of a simulation lecture. I initially planned to do this using MATLAB. MATLAB actually has a phenomenal control toolbox, so you can do all kinds of great control calculations in MATLAB. However, when I was putting together the lecture, this is what I was working on last week, and why you didn't get any lectures or you only got one lecture last week, was because it was actually becoming more complicated than I thought. So I kind of looked for an alternative, and luckily I found online this Excel spreadsheet for simulating a PID feedback loop, and it involves a first order process with a time delay. And so I did not make this spreadsheet, but I was able to pull it off a web page. I made a couple adjustments. Basically, I made the curves on the graph a little bit thicker so you can see them, but otherwise it's pretty much straightforward. So right now I have an open loop feedback loop, so it's in the open loop mode. And here I have a process, and so this is the first order process, so this is the gain. The lag is just a time constant, and right now we have no delay, and I have all the controller settings equal to 0 because we're not going to do anything with those. And if we look at our system, so the green, we're looking at a step input, and that's on the axis on the right? So it's going from 0 to 1, a unit step. And then the blue line, which is using the left y-axis, right, which is process value, we have kind of a first order rise, right? And we're going to a magnitude of 3 because that's our gain. And then when we go to the 2/3 part, right, so if I'm right around here, right, I click right here, and I see right at about time equals 20, right here's 21, right at 20, and right around the 2/3 point. So that kind of gives me my 2/3 response. And we've done this many, many times, so hopefully this is all evident to you. Now if I put a delay, so maybe we'll do a time delay of 5. And same as before, we have our first order rise, except now we have a delay where we don't see anything happen until we get time unit 5, and then we have our first order response. So unfortunately, this doesn't do second order systems or higher order systems, but that's not too much of an issue because most processes in the chemical industry are relatively well described by a first order process with a time delay. And so we can get a lot of information by just understanding this process. Also, things like second order systems, typically we don't have underdamped processes in chemical engineering. It's only when you put a feedback loop on it that it becomes underdamped. But the process itself is typically first order with a delay, which is really just transport. Think long pipes. All right, so let's go to closed loop, and let's try to design a feedback controller for this. So as before, we're going to do kind of the Ziegler-Nichols tuning rule. And so Ziegler-Nichols tuning is basically we can just set our gain. So let's just pick a really small gain, all right? And so let's just do 0.1. And what we see is as we go 0.1, we kind of have our rise. This is the blue. This is kind of our output, our control variable, which they call the process variable. Here's our step input, which is our set point, which is the red, right? It's a unit step point change. Ideally, the blue curve would go to the red curve, right, if we're going to track that system. And then the green is our input value. Now, right now we have the integral time and derivative time equal to 0. But if we want to kind of get basically rid of the offset, we can add integral time, and typically you want to go for a big value, right? Because remember, integral time, a big integral time means kind of a weak integrator. If it's too strong of an integrator, we'll go unstable. So let's just try 10. And when I do 10, I see that all of a sudden the system starts oscillating, and you actually see the oscillations are growing as a function of time. So this is actually too aggressive of a controller. So the system's gradually going unstable. So maybe let's cancel there. So let's come here. Let's try 50. And now we start seeing a response, right? So if I look at my process variable, I come up, nothing happens to time equals 4. And then kind of get the response. It's kind of underdamped, and it's converging to the set point value. So this is an idea of how a PI controller can give you kind of offset-free control. We could also try throwing in derivative time. Derivative time is a little bit weird. It's kind of tough to intuitively understand, but maybe let's try 1. And we get this kind of jaggedy stuff. This is because the derivative, but we kind of get the response. I'm not going to really talk about derivative time. It's not really used in the chemical industry because it's actually really difficult to figure out how to use it. So anyway, let's come back to the system. Let's go back to the 0.1. So in Ziegler-Nichols, what we want to do is gradually increase the gain until we get the system to oscillate. And that's going to be our ultimate gain. So let's try to figure out our ultimate gain. So 0.1 isn't not the ultimate gain. Let's try 0.5. Nope, we're getting closer to the set point, but we're still not there. Let's try 1. 1, we start seeing some oscillations, but we're not critical. Let's try 2, right? And now we have oscillations, right? Our system's oscillating, but those oscillations are decaying. So it's probably like maybe 2.2 would be my guess. And now the oscillations are growing. So that's a little bit too aggressive, but if we're probably around 2.1, we start seeing that our oscillations are reasonably stable, right? It's decaying a little bit, so maybe we can do 2.15 as our critical gain. Nope, still going up, so let's do 2.12. And that looks, let's go back 2.11, and then now we got stable oscillations. So again, we can now think about Ziegler-Nichols tuning rules, right? So if we want to do a PI controller, and that's normally the controller that we want to use, so what we're going to do is, let me pull up my calculator so I can figure out these numbers. So what I want to do is take the controller gain, and basically I'm going to divide that or multiply that by 0.45, but we'll do that in a second. Let's first figure out our integral time, right? And so what we want to do is just look at the peak of these oscillations. So right now here's one peak on the process variable, that's at time 74. And then I have another peak at time equals 94. So this suggests that the period of the oscillations is 20, right? So 94 by 74. And so what I want to do then is divide it by 1.2. So I do 20 divided by 1.2. And that's equal to 16.6 or 16.7. Now this will be unstable. And now what we're going to do is to kind of tune down the gain. And right, we have 2.11, and now we're going to times it by 0.45. And what we're going to get is 0.95. And we have 0.95. And when we get that, we get kind of our oscillation, a decently tuned controller. So we're going to still have overshoot. So we have our delay, we have overshoot. Sometimes you can't get rid of this. We have a quick oscillation, and it quickly delays, or quickly attenuates out, and we reach set point. And so that would be an example of using Ziegler-Nichols tuning to get a feedback control loop. Now, once you have this, we can play around with it. So maybe our overshoot is a little bit high. So one of the things we might want to do is maybe we can tune down the interval time or tune down the integrator. So maybe 16.7 is a little aggressive. So maybe we can try 20. That didn't really work. Maybe we can try 40. Nope, looks even worse. So 16.7, come back to what we had. And maybe we could try tuning down the gain, 0.7 here. And that might look a little bit better. So we kind of come back over here. But again, when we have the 2.11, 2.11 times 0.45, I should have written this down. And we got the 0.95. Right. We have kind of a standard controller. And this is typically what a feedback control response will look like. I mentioned you're always going to have the oscillations. This is due to the time delay, right? It introduces an infinite amount of phase, so it's very easy for oscillations to get amplified in the loop. So I'm going to stop there. I'm going to post this simulator on Compass. I encourage you to play around with it, and I encourage you to use it for your homework. So one of the problems I'm going to ask you to do is to use Ziegler-Nichols tuning, and this is just one of the ways to do it, right? So it's basically a trial and error approach. Obviously, on a real system, you're going to be much more cautious. It's going to take more time because you don't want to let the system go unstable. I should also mention that there's lots of kind of auto-tuning methods that a lot of PI controllers have built into them. So basically what these controllers will do is they'll start artificially introducing oscillations into the system. So basically it'll start oscillating the input. So it'll start kind of oscillating the input. And then based on kind of the response, you can back calculate out things like the ultimate gain, the period, and then use kind of Ziegler-Nichols tuning or any other rule based on that kind of information. And as I mentioned, there's lots of different rules for that. But typically, I should emphasize, except in high performance applications, a lot of tuning is done manually, right? Just kind of playing around with the different parameter values and then just getting intuition based on kind of process characteristics. What should the gain be? What should the integral time be? Where modeling comes into it, where a lot of kind of the analysis is when we do multivariable systems. And unfortunately, we're not going to have much time to talk about multivariable systems. And that's when we have multiple inputs that affect multiple outputs and we're trying to control everything all at once. All right, but I'll talk about that at the end of class. Anyway, if you have questions, feel free to post them on YouTube, and I'll do my best to answer them. And stay safe.